In this video I thought we'd have a look at some of the more detailed elements of the circuits used in the transistor processor. The overall design is based on some fairly simple building blocks, but when you start putting all these together in a complex system like a microprocessor, there are certain things that need to be considered as part of the design. You might be able to cobble something together that will kind of work, but if you want something that's stable, expandable and reliable, then you need to design it in a way that is going to ensure you don't get any weird timing issues. And it's really the timing across the entire processor that is the important thing. The individual circuits are fairly easy to get working, but overall you need to make sure that the processor is going to function the way you expect it to. Now, firstly, as in the previous videos, I've explained that this processor is based on a 5-phase instruction cycle, so that's 5 machine cycles per instruction. But if you've watched any of the previous videos, you'll have noticed that some actions seem to take place on single phases. That is, more than one thing happens on a single phase. Now in reality only one thing happens at a time in this processor, but it uses a dual phase clock, so there are essentially two separate clock lines, and they're around 180 degrees out of phase. So what actually happens is during each phase of the clock, so that's during each of the machine cycles, there are actually two events that can occur, one on the rising edge of the main clock and one on the rising edge of the inverted clock. And in fact you can also have events, and we do have events, that occur on the falling edges of the clock. So there are actually quite a few different discrete clock phases, clock edges that you can use through your design to decide when a particular event should occur. And it's making sure you get those correct edges sorted out that is important. Now in addition to that, you also need to make sure that the timing of the clocks as they arrive at any element within the overall processor is correct. And that's what we're going to look at in this video, because it's not as straightforward as it may sound. And this is the basic building block for the D flip-flop that we use in the processor. We actually use two forms of flip-flop. We use a JK in the counters, and then we use a D for the registers. And we use the D flip-flop in two forms. The first is a simple form, as we have here, single stage, and it's really known as a transparent latch. And the reason for that is because you apply data to the input marked D in this diagram, and when you apply a high level on the clock input, the value on D is effectively transparently transposed to the Q output, and obviously the not Q will be the inverse of that. The output will change in response to the input. So if the input goes low, the output will go low. If the input goes high, the output will go low, as long as the clock level is high. As soon as the clock level drops to 0 or low, then whatever value was present on the D input at that time will also of course be present on the Q, but that will be latched. So if when the clock is low the D subsequently changes, that will not affect the Q input. And that works fine as long as there is no chance that the output can in some way affect the input. So in other words, if the buffer is used in such a way that changing Q could change D, then you'd get this kind of circular race condition going on as long as the clock's high, and the output is then really determined by when the clock goes low rather than the actual data that you want to latch. So bear that in mind when you're using this circuit. If you want it to latch just so, for example, like the output register where the output's never going to affect the input, then it's fine to use a single stage. If you want to use the output in such a way that it could influence the input, you need to go to the 2-phase or the master-slave version of this circuit. So this is the master-slave version of the circuit. So it's actually just a duplicate of the circuit. So it's one transparent latch here and one transparent latch here. But as we said, if you have the clock level high, then the value at the output will be whatever the value at the input is, and it will change as long as the clock's high. And that means that you need to have the two clock inputs to the two stages inverted relative to each other. So that is, when the clock is high on the first stage, the clock should be low on the second, and vice versa. And what that guarantees is that it's a two-step process to get data latched on the Q output. So when this clock is high, the clock going into here is low. So in other words, this is no longer transparent, it's not latching anything. But the value D will end up here. And then when the clock on the first stage drops low, the clock on the second stage will go high. And then the value that's been latched into the first stage will be latched into will be transparently transposed to the output. But this has no chance now of affecting the input of the or the output of the first stage, because that's already been latched and the clock is low, so this is no longer transparent. Now this means that we need two clocks, or at least an out of phase clock, feeding the second stage. So one way of doing that is to just have an inverter sitting between the main clock and the output phase, or output stage rather. And that's what I did in the breadboard version of this processor. But because there are quite a few registers, and also this does give rise to some additional problems, so what I did is change to a true two-phase clock. So it's exactly the same circuit, except that the inverter has been taken out, and now we feed it with a two-phase clock. We have the main clock and then the out-of-phase clock going to the second stage without the inverter. So this simplifies the overall design, because it means you don't need an inverter in every one of these, and bear in mind there are 8 of these circuits in each register. So once we've done that, then that's simplified the need to have an inverter here, but it introduces other problems. That is that when you design these processors, you have to effectively work out what the timing and the skew is going to be across the entire design. So if you look at the transistor schematic for this, then you can effectively divide it into stage blocks, or stage timing blocks. So you'd have one stage timing block here, you'd have one here, one here, and one here. So in other words, this particular circuit would occupy 4 timing slots, and you need to make sure that anything that occurs in a given timing slot happens at the time you expect it to. Sounds like, what's this all about? What does it matter? Well, the point is, if you have a simple two-phase clock where the edge on the first phase changes at exactly the same time as the edge on the second phase, then because you've got a delay here, then what happens is this clock is effectively leading this clock, because the edges occur at exactly the same time within the clock generator itself. It hasn't taken into account the delay across this section, and we need to ensure that the delay across these two parts of the system is taken into account in the clock generator, to make sure that the clock edge occurring here does not overlap the apparent clock edge occurring here. It makes more sense if we look at the transistor version of the Latch. So if we then look at the version, the schematic of the version we actually use, then this is what we end up with. As you can see, it's a bit more complicated to look at, but it's essentially exactly the same circuit. The only thing I haven't mentioned is this line here, which is a reset, but it doesn't really affect the overall timing. It's just normally held in one state or the other, so you can, for the purposes of this discussion, ignore it. But obviously we have a significant delay in this circuit between the clock edge going high or low and the output changing. So we need to make sure that the two clocks that we're feeding have a proper timing relationship, and we need to do that across the entire processor to make sure that everything that happens, which is driven by the clocks, happens at the time we expect it to. And that's not necessarily, in fact almost certainly will not be, at the exact time of the clocks. So what we'll do is we'll look at the output of the clock generator, and I'll explain this in a bit more detail, but just remember this idea that there's a significant timing delay across any of the elements within the circuit. Okay, so we're now looking at the output of the clock and the not clock on the scope. The bottom trace is the clock, the top trace is the not clock, and they apparently are doing what you'd expect them to. The jitter is just because I don't have the ground lead attached on these two probes, so there's a bit of mains hum superimposed on the signal. So I've got this set on the slow clock, And it doesn't really matter what the clock speed is that you feed in up to a certain point. It's really the relationship between the rising edges and the falling edges that we're interested in. So although it looks like they are occurring at exactly the same moments at this point, they're actually not, and the circuit is specifically designed to make sure that they don't occur at the same time. In fact, if we look at the schematic for the clock circuit, what we can see is that we have a common clock signal coming in, and then there are two drivers. The reason I had to go for a totem pole type driver is because there are a lot of circuits connected to the clocks, and so these are driving about 50 other circuits or other inputs. So the fan out is about 50 to 1, so these need to have significant drive, and they also need to be fast edges, so that's the reason for designing a circuit in this way. It's also because it gives me the ability to control the relationship between the rising and falling edges on both ends of the clocks. In other words, rather than just skewing the clock one way or the other, this allows me to control both edges both edges of each phase of each clock. So we'll look at that on the scope. If we zoom into the signal, so as we go further in, firstly you'll notice that the edges are quite fast, but now you'll see that we are getting a significant skew in the signals, and that is intentional. This 2 or so microsecond delay is introduced by having the various resistor values in this circuit, and that was intentional. This is the delay required to allow the signals to propagate across the flip-flop stages. So in other words, we've allowed around 2 microseconds for the signal to propagate from the input of one stage to the output of that stage, and that makes sure that we're latching what we intend to latch and not what happens afterwards. So for example, if this input is from the data bus, if the clocks occur at exactly the same time, then because of the delay across the stage, we can end up latching the floating value of the data bus into the output of this latch, because the data bus will probably respond a lot more quickly than the propagation delay across this stage. Now, I've kind of gone a bit over the top by allowing 2 microseconds. It doesn't need to be anything like as much as that, but because it's a kit that I was producing, I wanted to make sure this was playing on the safe side. So not only do we need rising edge of the main clock to have a significant delay, so if you imagine we're looking at really the positive phases of the clocks is when things are going to happen. This arrangement makes sure that there's a gap between the falling edge of one clock and the rising edge of the other. If I change the edge that the scope's triggered on, you'll see that the reverse is true, that there's a gap here as well. So rather than these overlapping as they would the other way if we didn't purposefully introduce the delay, the not clock effectively, or the high part of the not clock effectively, sits within the low part of the clock, and that guarantees that we don't get any overlap. Now if you decide that you want to modify the circuits or the processor to run a lot faster, then this is the main thing you would need to change. If you think about it, on each clock cycle we've got 2 microseconds at each end of the clock in each cycle of the clock. So that's 4 microseconds of wasted time within the clock, and that kind of limits you, even if there's no other timing requirements, to about 250 kilohertz clock cycle. If you actually reduce this to about 50 nanoseconds, you can get the machine to run up to about 2 megahertz. But obviously you need to be very careful there that you don't go too far, otherwise you'll get very erratic and unstable operation. Now the other requirement was to have fairly fast clock edges to make sure that all the latches latch at the same time. This is just one latch within a register. In an 8-bit register, of course, you have 8 of these, and you need to make sure that the clocks on each one all occur at, relatively simultaneously to make sure that the data is latched as you expect it to. So if we zoom in still further and bear in mind that the latching occurs on the falling edge. So that is, when the clock's high, this is transparent and data passes through, and the same here, when this clock's high, data is transparent and data passes through. But it's when the clock level drops that the data is actually latched and will no longer change in relation to the input. So we need fairly fast falling edges to this, and that's again another part of the design of the clock circuit. So if we now look at this, we're getting about a 20 nanosecond or less than 20 nanosecond fall time for the clock, which is obviously very good considering the drive it's putting out. And so if I go back and we look at the entire clock again, although that skew is no longer apparent, it is still there, and it is a requirement for this system to operate correctly. Now, I've skipped over quite a lot of the detail of this. Hopefully you've got the general idea that it's the relative timing design that you need to establish first based on how you intend to organise the processor. And so that was the first thing I did when designing this machine, was to make sure that I had a stable clock regime so that the individual circuits, as I designed the circuits and added more circuits, weren't going to kind of incrementally introduce more problems, and that I had plenty of scope for designing the circuits and making an entire machine that was going to work in a stable manner. Also, you need to make sure that this is independent of clock frequency. So in other words, this is an edge system. It doesn't really care how long the clock's high or low for. It's really driven by the clock edges. You do of course need to have setup time for the bus and the latches and whatever, but that's fairly minimal. It's probably only 20 or 30 nanoseconds. So that's it for this video, the first of a few that I'll be posting about the circuits used within the processor. If you want me to explain any circuits in particular, then please let me know in the comments.